Point 2, miss penalty. In this part, we will learn this concept, miss penalty, and some other related concepts. All right, so first, let's look at the basic concepts in cash. First, cash concept. Here, so look at the description of the cash. Although we have the concept in our mind, but here let's look at its description. The highest or first level of the memory hierarchy encountered once the address leaves the processor. All right, so two parts. In this description, there are two parts. First, the highest level or first level, okay, of the memory hierarchy. Then look at the, more description, encountered once. There is a condition after it. The address leaves the processor. That means we do not count CPU register, because CPU register, that's inside the processor. When the address leaves the processor, out of the CPU register, the first level in the memory hierarchy, the cache level. So that's simple. All right, so no problem. Next concept, cache hit. Cache hit. So we can guess the meaning easily. When the processor finds a requested data item in the cache. Requested data item, but here it just mentioned the data item, right? When the processor finds a requested data item, is there another possibility other than data item in the cache, right? Is there other possibility, right? Another possibility is instruction. Okay, so data or instruction. Data or instruction, two possibilities. Sometimes we load an instruction from memory into cache. Sometimes we load data from memory into cache. So two cases. And another more general way to call here, just to call requested word. Requested word. The word could be double word, right? But we just say general word. Requested word. So later we will see this one. Because when we say requested word, it could be an instruction word, right? It can also be a data word, right? So it will cover both cases. Anyway, we just try to understand the meaning better, more precisely. The next concept, cache miss. Cache miss. When the processor does not find a data item. Here, same as the previous one, another situation, instruction. Because it's possible the processor need to load in, because the instruction thing is a little different from data. Instruction thing usually we load based on the sequence. But still you have the cache miss, cache hit cases, right? So we should include instruction case. It needs in the cache. All right, to get better coverage. Not just data, also instruction. We may have cache miss also, right? Next, our main concept of this part, miss penalty. When you get a cache miss, you need to pay penalty. So here, the description. So what is the meaning of the penalty you pay? The cost per miss is called a miss penalty. So what's the cost per miss? When you have a cache miss, you couldn't find it in the cache. You have to go back to the main memory to fetch either the instruction or the data item. Two possibilities. Yeah. But most likely the data item. So that's why here, mainly mention the data item. Yeah. Instruction miss rate usually much lower than data miss rate. Yeah. Later, when we work on concrete examples, we will see these two different type of miss rates, quite different. Yeah. All right. Okay. Yeah. Cost per miss is called the miss penalty. Per miss. So you load data from main memory into cache. That step takes a lot of time comparing with the cache hit case. When you have a cache hit, you just load data from cache to CPU directly. So that is very fast. All right. If you get a cache miss, you have to go back to the main memory to find the data item. So here I use that as an example, data item, because it happens more frequently. Yeah. And bring it back to the cache. Then the penalty. So here, let me give you an idea. What is the ratio, the time difference, the time scale difference? Usually 1 to 100. That's difference. 1 to 100. That big difference. So what's that? If you have a cache hit, you just use one clock cycle. Here, one means one clock cycle, CPU clock cycle. So you can get the data from cache into CPU. 100 clock cycles. If you have to go back to the main memory, then you have to pay 100 clock cycles. That whole trip from go back to main memory, find the data, and load it back into cache. 100 clock cycles. So you can see the difference. So that's the reason we say that's the cache penalty. In this situation, we say this 100, this number is the miss penalty. We have to pay miss penalty. Yeah. All right. Here, cost. Yeah, it explains about time of clock cycles. Yeah, usually it is more convenient we use clock cycles to describe the cost, miss penalty, needed to load data instruction. Yeah, here you can see data/instruction, right? Yeah, two possibilities. From the main memory into cache, where a data miss occurs. Yeah, so that's simple. Yeah. All right. So this is the miss penalty concept. Yeah. So now you know the reason. If you can avoid miss penalty, you can improve performance a lot, overall performance a lot. Okay. All right. Next topic, unit of data in cache. Unit. Yeah. Why unit? Because when you load the data from main memory into cache, what unit do you use? Right? So that's an interesting question. Data transfers between cache and memory should be in certain unit. So that unit, how big is that unit? It is an important question. We need to answer. Okay. Yeah. All right. The transfer unit, we give another name called a block, cache block. Okay. Cache block is the unit. How large is a cache block, right? How large is a cache block? So here we have this concept, block. concept, but how large is it? Yeah, so we will see that. Yeah. Block is a fixed size collection of data containing the requested word. See here, we use requested word, right? And more general, covering both cases. Okay, yeah. Called a block is retrieved from the main memory and placed into the cache. Yeah. So each time, yeah. So here, let me just draw this block. Suppose this block is this large, right? Yeah. Contains multiple words. Yeah. All right. Among multiple words, this is the requested word. Somewhere, inside the block. Yeah. Could be anywhere inside the block. Okay? Yeah. But you can see, although this particular word is requested, but when we load, we want to load more than just this word. We load the whole block. We load the whole block. That contains this word. So you may ask why we load the whole block. The reason is very simple. Because one trip from cache to main memory and get back to cache, that one trip is very expensive, 100 clock cycles. In that expensive trip, we want to carry not just the one word, that's not efficient. We can carry certain number of words together, and we hope other words could be reused later based on the principle of locality, right? Principle of locality. Spatial locality, right? Spatial, yeah. Memory locations, spatial localities. Based on that, in this way, we can reduce the number of trips from cache to main memory and reduce the number of missed penalties. So you can understand the reason is pretty straightforward. Yeah. All right, then let's look at the question. We need to answer the block size question here. The typical block size question. Yeah. A typical block size, 34 bytes, 8 double words. We know each double word, 8 bytes. Okay, 8 times 8. Okay? 8 times 8. 8 double words. Each double word, 8 bytes. Yeah. 64 bytes. Yeah. Typically, so that means the most frequently used block size is 64 bytes. But there is some possibility the size could be different, right? Yeah. Small percentage could be different. Yeah. All right. And in our questions, we will use this size. Okay. In all our computation questions, we will use this 64 block size. Yeah. All right. Next, the block size cannot be too big, cannot be too small. Yeah. So based on the experiments, people try many different block sizes. And finally, based on the statistics data, this one gives the best overall result. Why? So if it's bigger than that bigger, so each time you carry more words, it may not be good because your data bus. So when you send the data through data bus, right? Yeah. Bus. The bus has a bandwidth issue, right? Bandwidth issue of your data bus. If the size is too big, it cannot pass through the data bus one time, so it has to be broken into pieces and send it into the data bus multiple times, then you cannot get it faster. So due to the bandwidth restriction, the size cannot be too big. All right. Cannot be too small due to the efficiency issue. If it's too small, then you may need too many trips from cache to main memory, round trip, right? Round trip. That will be very expensive. So somewhere in the middle is the best. And that is the 64 number. All right, so we finished our 8.2 here.